Welcome, everyone. We have a great crowd tonight, so it's so wonderful to see that. Lots of students, which is always great. So thank you for being here. My name is Crystal Hopper Myers. I run the STEAM Pathways program
Welcome,
over
everyone.
here at SWOCC. A little bit of
We have a great
echo.
crowd
tonight, so it's so wonderful to see that. Lots of students, which is always great. So
Hold on one second. We're having a little bit of a technical.
My name is Crystal Hopper Myers. I run the STEAM Pathways.
We're streaming
program
online, so
over
please
here
bear with
at
us.
SWOCC. A little bit of
We have a great
echo.
crowd
tonight, so it's so wonderful to see that. Lots of students, which
Okay, go now.
sorry about that. We are live streaming. I did thankfully hit the right button this time. So we actually have online viewers right now. So if somebody wasn't able to make it tonight, or if they want to watch this later, they can actually go to our YouTube channel. So I was going to mention that. But again, I run STEAM Pathways, and I have the great opportunity to work with these awesome professors in this awesome health and science building. If this is the first time you've ever been here, please walk around, check it out. We have lots of labs to look at and various different things in this building. So I always like to mention that we have some amazing SPEAR SPEAR is the name of our team of student researchers that are always working really hard on various projects. We've had huge support from Oregon NASA Space Grant Consortium. We always like to say thank you to them for their help. They're currently helping fund one of our faculty research awards that are putting some of these students to work. So this is some great hands-on research opportunity for them, and great things that they'll be able to help them along their journey. We also have a recent partnership that we teamed up with the Oregon Coast STEM Hub, and which is helped and supported by Sea Grant and others for a new high school STEM internship program. So we actually have a couple of high school students that are helping us doing some research. So anyways, we thank you again for being here. We have a couple of lectures coming up that I hope that you can attend as well. One coming up so quickly as next Tuesday on the 12th at 6 p.m. We have a biology lecture with Dr. Carr. Dr. Stephanie Carr is actually coming all the way from Hartwick College in Winota, hopefully I said it right, New York. This was actually an awesome ocean discovery lecture series that I had applied for us to be a host to her talk. So it's a great opportunity to be able to meet her, and we're just grateful that we're able to host her here. And then on the 21st, we actually have Dr. Roman Gomez from the Southwest Research Institute in San Antonio, who will be giving a talk called The Physics of Anime. He'll also be giving you some updates from SWRI. We will try to do another reminder later on. If you didn't sign in at the front when you got here, if you would do that before you leave, it kind of helps us with tracking how many people attend these types of events. We would appreciate it. And with that said, I'd like to introduce our awesome chemistry professor, Derek Morelli, so that he can talk to you a little bit about our guest speaker today. Thank you.
Awesome. Thank you. So this is the second science talk I've been able to get behind, so I'm excited about that. And in trying to pick a speaker, I was actually inspired by a friend of mine named Jeff, who runs the Coast Cruiser Coffee. I think I said that right. But he sent me a YouTube video of a coffee YouTube channel by James Hoffman. He said, hey, you should check this out. It's really cool. And he just so happened to be interviewing Dr. Christopher Hendon. And during that video, I was thinking, man, this guy is from University of Oregon. It's right nearby. It'd be great to have him come and give a talk. So luckily reached out and he said yes. And a little background, He graduated from University of Monash in 2011 with his bachelor's and followed up with a PhD from University of Bath, and then had a 2-year postdoc at MIT. And immediately after that, started working at University of Oregon. Since working at University of Oregon, he's published lots of papers. He's published a book called Water for Coffee. He's been honored with being an amazing scholar, educator, science communicator, many things. So hopefully we will get to experience all of that tonight. So it is my pleasure to introduce to you Dr. Christopher Hendon.
First of all, thank you very much for the invitation. Crystal, thanks for organizing everything. And for all of you, thanks for making time in your evening to come and talk about coffee. Usually we'd have coffee with this talk, but at 6:30 or 6 o'clock, it's a little reckless. So I want to first start by highlighting a couple of people who do all the work. So this is my research group at the moment, and I do want to point out Julio specifically. So Julio actually transferred into the University of Oregon from Lane Community College and then joined my research group. And I want to encourage you, some of the audience may be interested in taking that pathway too. Maybe not UO, but just think about it generally. There's a lot of different types of chemistry. I'm going to show you some of it today that applies to coffee, but there are a lot of different pathways you can take. And a community college degree is a really valuable one. So I'm really excited to be here. It's my first time at a community college giving a seminar, and it's really a pleasure. So thank you very much. A lot of the work is also done today by Robin. So Robin just recently received her PhD. It's the first PhD in coffee electrochemistry, I think probably ever. So this is going to be some new stuff that I have not really talked about before. Okay, my lab looks like a cafe. It's in the middle of Willamette Hall. There are no walls. We've had nothing stolen because Oregon's a nice place. So it's a perfect place for creating something like this. It also means that the students, there's a high demand on them because they're working in public. People are watching them and engaging with them, talking to them about their science all the time. And that was the original idea, was to create a space that really was sort of a safe space to engage people in science, but over a cup of coffee. We also happen to be studying coffee. And so you can see here, this is the lab, and you're welcome to come by anytime. We do a free coffee tasting every day from 11 until 12, and it's whatever experiment we're working on that day. We're just going to open it up and drink all of it with you. So if you ever happen to be in Eugene, even if it's not between 11 and 12, let me know, because I love sharing coffees with you. I have a bunch of really nice coffees available. Well, let's go back a step. So as we learned, I did my PhD in Bath, and this is the Roman baths. The city is named after the Romans who founded this place. This place has unusual water. The Romans thought that it was therapeutic. They would drink it and would cure some ailments. Indeed, there was unusual water, but the thing that was unique about Bath for me was that because of that water, high-end coffee shops started popping up all over the place. And in particular, one I would frequent on my way to work was Kalana and Smalls. And this is the menu that I was greeted with. Now, seeing these today is more common than it was back in 2011. But what you can see here, this is the photo of the day that I got interested in coffee, is that you can see that on this side, there's espresso drinks. On the other side, there's filter drinks. These are sort of drip coffee, or something you'd be more familiar with in the American market. And then there's also other words you might be familiar with, like the country of origin, and perhaps even the processing method, washed or natural, and flavor notes. And when I started seeing these flavor notes, I wasn't sure whether for example, Brazilian coffee that tasted allegedly like fruitcake was because it was from Brazil, or whether it was because it was from that particular farm, or whether it was the natural. And over the years of drinking lots of coffees, I started to get an understanding for what these words mean. But if you think about what the flavor notes are, they're really a contract. Right? You walk into a cafe, and if someone tells you that you're supposed to taste lemon peel, watermelon, and bergamot, and you don't, is it you that's the problem, or is it the coffee that's the problem? Worse is, what if it actually is supposed to taste like that, and then one day it tastes like salmiakki, which is a salted Finnish licorice, dirt, and Brussels sprouts? I would say that contract has been violated. Then that's bad for everybody. It's bad for the specialty market that tries to push a product on you that's supposed to have well-defined and desirable flavor notes, but it's also bad for you as a consumer, right? Because you've spent some money on this. Well, it turns out a lot of people spend money on this. So the coffee market in the United States is actually now up to 1.9% of the US GDP. It's a staggering number. And in the United States, filter coffee dominates. When I say filter, I mean that if you were to weigh the mass of coffee dissolved in the water, it would come out at about 1.2 to 1.5% by mass. That's about 10 times more dilute than espresso. So espresso is something like, let's say, 8 to 12% by mass floating around in the cup. And Europeans tend to drink this, Americans are in this space. But the thing is that independent of whether you're brewing it small or large and more dilute, it really matters a lot that it tastes good for particularly countries that produce it, like Burundi, where 25% of its GDP comes from coffee production and 90% of its population work in that space. So we have an obligation as a consuming country to do a good job of making Burundian coffee taste good, because you basically can destroy the entire country if they have a bad year. So it's really, the type of work we do may seem somewhat incremental as we're moving forward and understanding how to make excellent coffee, but it's a really big deal for a lot of producing places. Now, if you were to break down what matters in producing excellent coffee, you could probably draw a pie chart something like this, where much the same as any agricultural product, if you buy high quality agricultural product, that's going to take you about halfway to having an excellent experience. It's the same with buying flour and making bread. It's, these things are common. And this, for coffee, you buy high quality green coffee, you're halfway there. But then you have to turn it brown, so you have to roast it. And so there's an artisanal aspect to that about how you choose to apply heat to turn it from green to brown. But the roaster is also then tasting the coffee after they've roasted it. And they're tasting it with the water that's available to them, whatever they've done to that water. So the water chemistry plays an equal role in determining the roast, because they're going to say it tastes good for their water. So we give that a 50-50. And then finally, the last piece here is the equipment, which is the part that's hard to understand, because that's the part that we all see. We walk into a cafe and we see a fancy espresso machine and a barista. I put a human, the barista, as part of the equipment, right? So this part is the least important part in the entire process. And somewhere between green to brown, there's also this whole other logistics issue of moving a lot of an agricultural product from a producing country to a consuming country. And so there's a big change in quality from this moment to this moment, okay? Now, I want to go back to this point here. So we could spend a lot of money on green coffee. You could roast it with the highest end roaster you want, and you could dial in the water however you like. But it turns out, of course, you can always spend more money on equipment. I'm going to show you the most egregious and most expensive piece of equipment I happen to own. I didn't pay the money for it, but this questionable looking object is the cup that Don Pettit, NASA astronaut currently on the ISS right now, developed. So this cup actually can pump water in space. And you think about this, is that with no gravity, water should go and form spheres and float around everywhere. So how do you get it to go to your mouth? Well, along this sharper edge here, what ends up happening is the water will wet along that edge, pooling right here. You bring this part to your mouth and you suck, and you're able to drink coffee in space. They spent $1.6 million developing this cup, and it works just fine. And it did incrementally make the astronauts' lives better, I guess. But you don't need to spend that money, because the industry actually has coalesced around this method for brewing. You start out with a cup that has a well-defined volume. You put ground coffee in it with a well-defined mass. You pour water on it. You wait for 4 minutes, and then you taste it with a spoon. And this is what's done for every single cup of coffee you've ever had in your entire life. It's been cupped. We call this cupping. It's been cupped multiple times. One when they decided to buy the coffee, one after they've roasted the coffee the first time, and then one after they do production roast. So along the way, people are tasting coffees in multiples to make sure that this cup, and this cup all taste the same. There's no defects and variation. And it works really well because no longer are you beholden to having excellent equipment. You can do this on the farm. And so this is basically how all coffee has come to be, how it tastes today. Now, what tasters are looking for is terroir, or whatever the environmental impact of creating that excellent product yields. We have a score sheet to grade these things. Now, it doesn't necessarily mean that scoring high in all these categories makes an excellent cup to you. Okay, this is really important. We just have to score it somehow. And I want to highlight one panel that really matters in tasting coffee, which is perceived acidity. Now, you may not like, for example, pickles because they may be too sour, but do appreciate that the coffee industry does value high acid. And so if you don't like that, great, you're going to save a bunch of money. But if you do like it, you can see very clearly here that we put more points on high acidity. And so This actually is the beginning of my journey in coffee, is that we went into that cafe that I showed the menu to at the very beginning, and we were not tasting acid in coffee at that moment. And that got us as scientists and also as the baristas who are working there thinking it's probably something in the water. And that gave rise to us writing this book, Water for Coffee. And I'm going to do my best to summarize it for you in 2 slides, okay? So water, H2O, is never pure. It's really good at dissolving stuff. And in particular, it's good at dissolving minerals from ground contact. It just exists in a reservoir and you're going to dissolve some minerals. And by far the most prevalent ones are calcium and magnesium, and those are positively charged. So for every positive, there must be a negatively charged species. You're typically going to find chloride, particularly near the coast. You're going to find chloride. You're going to find bicarbonate, which ends up yielding lime scales. Anyone from California probably is familiar with this. And it turns out that bicarbonate is the bad actor here. So bicarbonate is the example that we use to teach general chemistry level acid and base buffering. Its role in your body is to prevent pH swings so that you don't have a rapid decrease in pH and your heart fails. And in water, it's trying to keep pH roughly about 7. So if I start brewing coffee with water that's rich in bicarbonate or high in minerals, what ends up happening is that the bicarbonate basically turns off the perceived acidity, and you're unable to then enjoy that cup with acid. And so you can imagine it's starting to score lower and lower in that score sheet. I'll show it to you in a graphic. On the left-hand side is the flavor wheel available. These are the flavors that I guess tasters have decided could exist in coffee. And on the right-hand side, you can see with increasing carbonate hardness, or more of that bicarbonate that I just showed on the previous slide, particular panels are falling out of this wheel. These are the panels whose flavors are driven by acidity. Fruits, acids, that sort of thing. So if you have high mineral composition, you typically are going to be unable to perceive fruitiness, acidity, even some of the nice aromatics. And this gives rise to having relatively low quality experiences in super hard water locations. So that's water for coffee. And that got us thinking, okay, so we don't really know what's going to be in a particular coffee. We do know that if we control the water, then in principle, we should be able to taste excellent flavors in whatever happened to be contained within that coffee. So now we need to start thinking about how we would measure what's in a cup of coffee. To do that, I need to give you a bit of a crash course on the state of the art in the coffee industry as it stands today. So let's go back to the Nobel Prize, 1907. This is the 6th Nobel Prize awarded in chemistry to Buchner for the discovery of the enzyme. And it's an important discovery because, of course, it's basically the first observation that there was something smaller than the cell. So if you broke the cell apart, you could still function doing something like this, fermentation. So what I'm trying to show here is this is a Pinot Noir barrel that is undergoing fermentation. And one of the things you'll note with grape juice turning into wine is basically you start out with sugary water, and over time, it's going to convert to ethanol-y water, alcoholic water. And you can monitor that with just a measurement of density. So the white dots here, you can see this is sugary water. It's pretty high density. After about 7 days, the density plateaus. And after about 7 days, you've consumed most of the sugar and turned it into ethanol. So some of us have probably home brewed and noticed this before. That it takes about 7 days to get the fermentation close to completion. Now, it's not done yet, but it's close. One of the observations that was made was that you could take a measurement of the refractive index. The refractive index you can think of as like the relative optical density, and it more or less tracks along with density. So you can see that as we convert sugar water to ethanol water, the refractive index also plateaus roughly at around 7 days. And this got the coffee industry excited because I think, well, why don't we just use the refractive index to make a measurement of what's in coffee? The problem with this is that the refractive index depends on the molecule that you're measuring. I'll give you an example. Molecules like sugar, they affect the refractive index differently than that of ethanol. So I could have a liquid that has 4 weight % ethanol in it, and it would have the same refractive index as a cup that has 1 weight % sodium chloride in it. And so this device would not be able to tell you whether you're about to have a 4% alcoholic water or whether you're going to have a cup of salt water. That's a problem, and yet the coffee industry has decided that this is the device we will use. So this is the manifestation of it. You put coffee on there, and then it's going to measure temperature of the liquid and refractive index and do some sort of math to report then a concentration in total dissolved solids. Now, I've already introduced you to this value before. This is that 1.2 to 1.5 weight percent coffee in the filter cup of coffee that Americans tend to drink. This value also is the y-axis here. You should think of this as concentration, how strong a cup of coffee is. And the device somehow actually gets it basically right. So the refractive index does seem to capture the ensemble or collective concentration of all coffee stuff in the liquid. But the industry went one step further. They said, okay, well, if the cup happens to be 1.3% concentrated, and that 1.3% came from extracting 20% of the mass into the cup, and I'll give you a mathematical example of that. If I use 20 grams of coffee to start and I extract 20%, I'm going to get 4 grams of that coffee out of the dry mass floating around in that cup. So I now have 4 grams floating around in the cup. And if I then dilute that by some amount to get it to 1.3%, then we're going to hit an ideal tasting cup of coffee. So hopefully you can appreciate that's how the industry uses this, is they take a simple measurement here, they plug in the brew ratio, the amount of water and coffee they use, and they rapidly can determine whether that cup's supposed to taste good or not. And yet, every single person in the industry, not a single person in the industry would tell you that every single time they hit this ideal mark, it tastes good. And the reason is because you don't know what 20% of that mass is that you're extracting. And the easiest example is if you brew hot and you brew cold, they taste different, and you could still extract the same amount. Okay, if you want to hear more about it, and you're not going to be bored of my voice by the end of this talk, I do have a podcast, okay? And in episode 14 of the podcast, we go into deep detail about why this is erroneous and why we need to move on from it. I'd encourage you to look it up. I've also learned something in this process. If you put periods in the name of your podcast, it makes it almost impossible to find. So, so in season 2 of the podcast, it will have a new name. It'll be called Coffee Literature Review. Excellent. Okay. But I'm not done talking about this yet. We need to do a little bit of thermodynamics and kinetics to understand really why this is a problem. Let's do an example based on the first Nobel Prize in chemistry awarded to Van't Hoff, 1901. Van't Hoff discovered that the extent to which a chemical reaction will proceed depends on temperature. That's probably intuitive to a lot of you. If you heat something up, sometimes it goes faster and further. And I'll give you a really easy example of that. If I take coffee, dry mass coffee, and I pour hot water on it, and I wait for about 10 minutes, I'm going to be able to extract about 15 milligrams of caffeine per gram of coffee I used. But if I use cold water, room temperature water, and I do everything exactly the same, I'm only able to get about 9 milligrams of caffeine per gram of coffee I use. And I can sit there and wait for as long as you want, and I will never be able to push this value up to there unless I heat it up. And this is because if a reaction were to proceed forward with increasing temperature, we would say that that reaction is endothermic. It requires heat to move it forward. Not every chemical reaction requires heat to move it forward. In fact, one very specific one that we teach people is when you're dissolving acids in water, always add the acid to the water because acids dissolve in water and release heat. And if you do it the other way around, you can boil the water off rapidly and it'll explode in your face. Well, that's problematic because I want acid in my coffee. And so as you can see here, caffeic acid, it's within the region where I can't tell that there's a temperature dependence, but you can very clearly see at minimum that caffeic acid's extraction is not really dependent on temperature. So you do have to appreciate then that if I change brew temperature, I can change wildly the relative populations of molecules that end up dissolving in the cup. One conclusion, if all you took from this talk for the remainder of the talk is the following, that would be a success. If you make cold brew coffee, it is not inherently higher in caffeine than hot brew coffee. You can make it stronger by making it more concentrated, but you are more inefficient or you are less efficient at extracting caffeine using cold water. Okay, good. We've got that one out of the way. At this point, more temperature gets endothermic molecules out. Acids are exothermic, so at high temperatures, in principle, you get less acid in the cup. You get the point that this is already getting complicated. This is thermodynamics. So this is imagining the reaction could go to completion. But in coffee brewing, we don't have infinite amount of time to sit around waiting for the cup to reach equilibrium. Quite the opposite. We actually need to brew it quickly, and espresso is the worst offender of this. So you can see here, this is a heavy molecule with a nominal 1+ charge. This is a light molecule, and what we're doing is monitoring how much of it is coming into the cup as a function of time. So espresso is brewed in about 25 seconds. And so you can see here, this one, we very rapidly start to extract all of it, and then we're depleting the coffee of it. Whereas meanwhile, this one is still making its way into the cup. And there's this sort of induction period where it's ramping up because the coffee doesn't instantaneously get wet. It takes time. So what if I dial it and I like the flavor in red, where I stop the shot at about 25 seconds, we've depleted most of this, we're getting an appreciable amount of that, and a different barista comes along and says, I liked it at about 12 seconds, where we got a bunch of this and basically none of that. So you can appreciate then that time also allows you to control relative populations of these molecules. Those two things together are a big deal because we know that the rate is affected by temperature and the concentrations are affected by temperature. And yet we know the device that we're using to measure what's in coffee cannot measure the molecules, but the molecules must be changing. So you'll appreciate this is a big problem. And yet in 2020, right before the COVID lockdown started, we published this paper in Matter where we developed this mathematical model for simulating espresso extraction. And importantly, we parameterized it with things like the particle size, the depth of the bed, and the geometry of the basket. This is just supposed to look like an espresso basket, okay? In order to get the right particle size, we had to then make some measurements. Here's a scanning electron microscope image of ground coffee. It's a little ominous looking. There's some holes in it. That's where the cells used to be, and we've roasted away the insides of the cells and dried it all out. So there's some pores, but nonetheless, in the model, we approximated this big piece as a sphere and these little pieces as little spheres. It's the best we could do at the time. And it actually worked okay. But the problem was that so we're monitoring that extraction yield, which was the x-axis before. We're grinding finer and finer, and we're getting more and more out of the coffee. And our model is this blue dot. So it's saying, yeah, we should grind finer and get more out to a point. But then experimentally, we realized, well, the thing is you start seeing this tipping off point where no longer are we able to extract as much as we would have expected. Okay, so that's a problem. And it's even more of a problem if the barista tells you they like it here. But I got a mathematical problem for you. I just spent ages telling you about how we can control temperature and all these other parameters and change molecular composition. But yet I had to parameterize this model somehow. So I took one diffusivity constant, which you can think of as like the ability for all of us to leave the room. And now some of us might leave the room faster than others. Well, I didn't account for that, okay? So I took one diffusivity constant and one rate constant for which that might occur. In other words, I did exactly the same mistake that device has built into it. It's an ensemble measurement. It's an average of all things. And worse was you didn't have to look very far in the literature to realize that the diffusivity constant for a very specific molecule in coffee, caffeine, this value and that value are not the same, which means that my average clearly is already missing the one that we actually know, and yet it still worked. We have to do better than that. And I promise you, by the end of the talk, I'll show you that we did better than that. The other thing that's worth noting here is that small pieces and big pieces are made of the same stuff, but they get wet. If you think about like the middle of the particle, they seemingly get wet at different rates. Now, they are actually getting wet at the same rate. It's just this one's bigger. But in effect, what ends up happening is the center of this particle here is not at all wet by the time this little one is starting to extract. So one thing you might then try and do is make all the particles the same size, but coffee grinders are inherently bad at this. And so we did our very best to account for it. But one strategy that you can use to actually try and get particles the same size is just to freeze the coffee and grind it while it's frozen. Now, I'm not going to tell you the physics behind this in detail, but I'll just simply say that coffee undergoes a glass transition at freezer temperature. And at some point, you can see at room temperature, it's got this hip on the particle size. And as soon as you get it to freezer temperature, it becomes much more like a nice skewed Gaussian. And if you cool it down to liquid nitrogen, all those really small particles become more or less the same size. So freezing coffee seemed to be a good thing to help us make more reproducible coffee. We published this paper, and I didn't realize that people would actually care about this. And now there are people building entire cafes around freezers built into their cafes so that they can access that very small difference between having that hip on the particle size and not having it. And so this cafe is one of many that have done this. Now, I want to take a side moment to highlight what this picture is. In the background, this is Kyle Ramage. He's a U.S. barista champion, the best coffee maker in the United States in 2017. And he approached me and said that he wanted to use this freezing of coffee thing for his championship routine. He inevitably won the United States and continued on to come fourth in the world just from freezing coffee alone. So we're talking very small differences that you can implement in your house, and it makes clearly a big difference in terms of flavor perception. Okay, so at this point then, two things you could do that you could take home. Number one, you could put your coffee in the freezer and grind it while it's cold. That's going to be a good thing. Okay, and number two is that if you don't like acidic coffee, you're going to save yourself a bunch of money. But this didn't help us, right? So this didn't actually tell us what's in the cup. So I started then for the last 4 years trying to figure out how I'm going to measure that. And it turns out that that's been extremely difficult. So we're going to start the talk now. Okay. To make reproducible coffee, you need to make sure your grinder is producing the same particle size distribution every time. And ours do that. But the problem is, as I showed you, at some critical tipping point, when we grind too fine, we get variability and no longer is all the water touching all the coffee evenly. And we thought, oh, it's probably some sort of clumping. It's like little pieces are forming a really dense region somewhere in that espresso basket, and no longer is the water touching it evenly, so it's going around that dense region, and we're leaving coffee behind. Is there a way that we could solve this problem so that we could just get into being able to make reproducible shots so that we could measure what's in them? Well, it turns out we were right. It is clumping, and the origin of the clumping is the same phenomenon that you observe when you rub a balloon on your head. So it's called triboelectrification, or also known as static. Basically, what happens here is you have solid coffee. Fracturing will create static, but also rubbing on the metal burrs in your coffee grinder creates static. And anyone who's ever ground coffee in their house clearly knows that grinding coffee makes a bunch of static. It sticks to basically everything. Well, it also sticks to itself. And so here's a microscopy image of a big piece, which typically charges positively, and little pieces here that are stuck to it that are formed during grinding that charge negatively. It is these clumps that were giving rise to inhomogeneous flow or uneven extraction. But the question is, how do you turn them off? Well, one very effective strategy was actually posited on some chat forum that I had to go deep dive into back in 2007. And it was a home barista named Ross who had proposed this idea that adding a very small amount of water to the whole beans before grinding would yield coffee that did seemingly not have static formed during the process. So we took all different coffees, dark roasted coffees that typically charge negatively, light roast coffees that typically charge positively, and started introducing very small amounts of water. We're talking like a little aerosol sprayer, just one little squirt of water. And as you do that, you can see that the charging of the coffee progresses towards zero. And you might think, oh, it's getting really wet. Are you not just forming big clumps because it's wet? That's not what's happening. So if you take a look at the particle size distribution using laser diffraction, you can see that without any water, there's this really long tail of big pieces. But even with just the smallest amount of water that you add, this tail very rapidly decreases. And what you see here is an increase in this particle size and a little uptick down here. In other words, those clumps deaggregate. The little pieces are now free-flowing, and the big pieces are free-flowing. Okay, so if you were to do this in your house, you squirt a little water on the whole beans, the first thing you'll see is that it won't make static at all. So I've just cleaned your kitchen for you, I promise. But if you actually do this in a cafe, and all you do is add one squirt of water to the coffee, and monitor the flow dynamics of the espresso as it's moving through that bed, as well as the concentration of coffee you get out of that shot, you get these two findings. So first thing you'll see is by adding a squirt of water, the shot time goes from, let's say, 35 seconds to 40 seconds. That makes sense. The particles got a little smaller, so it's slowing things down. But the other thing you'll note is that with a simple addition of just a tiny little bit of water added, the concentration of that espresso shot goes from 7.75% to 9.05%. In other words, let's say roughly 20% increase in coffee concentration from the addition of 10 microliters of water to the whole beans. This is an enormous deal. This is a absolute game changer, because what we're talking about is now being able to use 20% less coffee for every single coffee made. This result was what got me on that YouTube channel, because this has actually had meaningful impact in the world. By implementing this, Starbucks has already saved $300 million this year. So it's not a small finding, but you can appreciate that I don't want to help the big company. I want to help the farmers push their quality up, and being able to access more of their coffee more evenly is better for them, because we can now get more of the good flavors out and leave more of the bad flavors behind. So this is a nice result because it helps basically everybody. Hopefully it also helps you add a little water to the coffee. But at this point, you can appreciate that we're now able to make higher quality extracts more reproducibly. And that got us thinking, how can we finally measure what's in the cup? To get to this, we have to go through 6 more Nobel Prizes, but I'll keep it short and just say the Nobel Prize in 2019 was awarded to 3 scientists for the discovery of the lithium-ion battery. We're going to talk a little bit about electrochemistry and the lithium-ion battery and how it applies to coffee here in the remainder of the talk. But first, let's start with some sort of electrochemistry crash course. Electrochemistry is defined as any chemical reaction where the reactant or the product is an electron or electricity, right? And so the most simple example is if you have acidic water and you provide electricity to it, you can make hydrogen gas. This is an important reaction. If you want to move away from fossil fuels, this reaction is what allows you to do that. You make H2, and that becomes one of the fuel sources. By definition, we call this reaction, it occurs at 0 volts. Now, of course, to actually do it, you need to apply voltage, but appreciate that this is what we're going to call 0. Relative to 0, there are chemical processes that could be aligned to it, and if they have a positive value, then they occur spontaneously. If they have a negative value, they are non-spontaneous. So you can see here that iron 2+ plus some electrons goes to iron is non-spontaneous. Let's go back the other way. Iron going backwards to form iron 2+. That would be plus 0.44 volts. That is the process of rust. So iron will spontaneously rust because it will release electricity to form iron 2+. Zinc right here will rust even more. So it'll create plus 0.76 volts going from zinc back to zinc 2+. And you've seen this before. So a galvanized nail is a nail that's made of iron, but it's been dipped in liquid zinc. And as soon as you pull that iron out of liquid zinc, it's now exposed to oxygen. So the zinc will spontaneously rust, forming that white powder that covers the nail. That is zinc oxide. And that zinc oxide forms a protective layer around the iron nail. No longer can oxygen find iron. And so the iron nail stays unoxidized. It will not rust. So the manifestation of this right here is that you can build a house in a rainy environment. Sure. And the reason it works is that zinc 2+ is quite stable, and this process is more favorable than this process. Who's seen Breaking Bad? I got to see a show of hands here. Okay, a lot of people. Season 1, episode, I don't know. You remember they break down because he leaves the key in the ignition. They need to get this meth cooking van back rolling again. Had dinner with this chemist who actually was responsible for all of the chemistry in the show and got to talk about this particular example in detail. I've just talked to you about the zinc nail, so you already know half of it. Well, what they kind of took the creative license here with this. They basically said, okay, let's imagine the galvanized nail still has some zinc available. If it does, then we can, in principle, generate 0.76 volts from that zinc. Now we need to find some other metal that's happy to also take those electrons and create electricity. And they found mercury 2+ going to mercury creates 0.85 volts. So if you strap zinc to mercury 2+, that in principle gives you 1.6 volts. They claimed in the show that they got mercury 2+ from mercury oxide in brake pads. That's obviously problematic. It used to happen. We used to make brake pads in the 1920s out of mercury oxide, but That would mean that every time you pushed your brake, you would be spraying mercury into the environment. So we quickly learned that was not a good idea. This van may or may not have had brake pads from 1920 on it. I don't think so. But if you strap 6 of these together in series, you're able to generate about 9 volts of electricity, and that's enough to basically jump your car. This is electrochemistry. And we're going to do the same thing, but we're going to do it on coffee. So I mentioned then that if you just stick a piece of metal into acidic water, you should be able to generate hydrogen gas. And it works really well for platinum, for gold, graphite, these sorts of things. So I'm going to be talking about platinum now, but you can imagine any inert metal. If you don't use an inert metal, then the metal could in principle rust like the iron. And so you end up with iron just going into your coffee, and that's not good. So you need to use something that's not going to react. Okay, so this is the reaction that typically happens. And I'm going to try and step through this and show you how we're going to use this and what we measure. Okay, so acidic water here, this is water, H2O, and acidic water has hydronium, which is H3O+. And if I start to apply a negative voltage to platinum, then the positively charged things in solution are going to be interested in binding to platinum. If an electron flows in the circuit, we measure current. So we're controlling voltage here. This is the x-axis here is voltage, and we're measuring current. So the first thing that might happen is we start to accumulate electrons in the platinum, and you see that the water started to orient so that the hydrogen is pointing down towards the platinum. The next thing you'll see is that hydrogen will start to transfer onto the surface, and when that happens, current flows. And at some point, we're going to get a complete coverage of that piece of platinum with a single atomic layer of hydrogen. And if we keep applying more and more negative voltage, I mentioned that we could make hydrogen gas. And so that's how we would do that. What's neat about this is that we can cycle backwards. So we can then polarize this piece of platinum positively. And in principle, all the hydrogen will come back off again and go back into the liquid. And so what's neat then is that we call this cyclic voltammetry, where we're controlling the voltage and we're doing it in a cycle where we sweep from plus to minus and back to plus again, as if we hadn't touched the liquid at all. This has actually been known since 1973. So early on in the sort of early 70s, people were using this particular reaction where you just sweep the voltage of a piece of platinum in water to purify water. And what you'll see here is that you start out at around here, you sweep negatively, you deposit some hydrogen, you come back, the hydrogen comes off, you go this way, you deposit hydroxide, you come back, hydroxide comes off. But if you kept going around and around and around, the amount of current that was passing seemed to decrease. And the reason it's decreasing is because impurities in the water would stick to the platinum, blocking the surface that was available for the hydrogen to stick. Let me draw it for you. Stuff that's not water, that's in water, coats the platinum surface. So if you stuck a piece of platinum in water and swept the voltage around and around and around, it would bind up all the impurities, and then you could, in principle, drink more pure water. And it got me thinking, what is coffee? It really is just dirty, acidic water. So this should work really well for measuring stuff in coffee. I'm going to try and show you a picture of it at 3 different length scales. So this is the length scale of the lab, where this is what we're measuring. We're going to measure current and apply a voltage. This is a picture of the electron energies in the very specific molecules. And this is a picture of roughly what we think is happening at that electrode surface when I stick a piece of platinum in coffee. Coffee's water with some stuff in it, caffeine, chlorogenic acid, other things. Now, if I start positively polarizing the platinum, okay, at some point, the energy of the platinum is going to be sufficiently low that molecules nearby are going to dump electrons into it. In other words, you're going to undergo that oxidation reaction that I mentioned, where these molecules here are going to lose their electrons into platinum, closing the circuit. So we see current pass. And what's neat about this is that it converts a molecule like chlorogenic acid into something like catechol, another organic molecule. Who knows what that tastes like, right? It doesn't matter. But what's neat about this then is that if I then sweep backwards, in principle, I could dump those electrons back into that catechol so long as that's still nearby, returning it back to the chlorogenic acid that it was in the first place. And then we'll go back to the very starting point where we were in the beginning, as if I hadn't affected or changed the cup at all. So by moving very quickly with this change in voltage, we're able to detect different compounds at different voltages, but not grossly affect their populations, at least not at this point. Now, I didn't talk about touching caffeine. If I wanted to get out there, I'd seemingly need to go even more positive, and you'd see that as a separate bump. So what I want you to take from this now is that in principle, if I apply different voltages, I should be able to see different families of molecules, and the current, the amount of charge that passes, is a direct measure of how many there are. So what's in coffee? Should be easy. It'll go. All right, we'll just skip to the end of that. It goes forever. And yet what you care about is this. You care about flavors. And we talked about water at the beginning and how it wipes out these flavors. Not every coffee has all the flavors, but like, for example, a coffee that may taste like blueberries, you want to make sure that you can detect that blueberry flavor, but we don't know what that molecule is. The only thing we do know is that certain molecules respond to applied voltages in families. So for example, phenolic compounds tend to oxidize between 1 and 2 volts. Other molecules that are in coffee, like for example, carboxylic acids, which are all of the acids that you like to taste, they show up at -2 volts. They're so far apart, we should be able to measure one and then separately the other one and not have to worry about them interacting with one another. And so what's it actually look like when we do it? Well, we make coffee and then this is a piece of graphite. We just stick it in the coffee. And then back here, we don't need to talk about the reference electrode today, but just appreciate there's a piece of silver in there. And then over here, there's a piece of platinum behind. And the lab has a rule. So the rule is you have to drink the experiment, okay? It's a little bit of a different rule than the rule you'll probably have to follow here. But in our lab, we're cognizant of the fact that we're doing chemistry that applies to a really big industry where people are drinking the product. So we must do things that are relevant to them. Otherwise, no one will ever do what we're talking about. So I assure you that this, although it looks a little janky at the moment, it is definitely safe. And also, I'll assure you that I'm not the first to think about it. So people had already been doing this. In 2016, people were applying a voltage. So this right here is differential pulse voltammetry. You just apply a voltage and measure the current. And you can see here that they were measuring chlorogenic acids, this compound right here, with differential pulse voltammetry and getting basically the same values, the same resolution as performing high-performance liquid chromatography, which is sort of like the Rolls-Royce of analytical chemistry. HPLC takes 2 hours to run. It's $100,000 to buy that piece of equipment. This is powered by a AA battery, and it takes less than a microsecond. So obviously, I was excited about that. And I was thinking, oh, it's going to work really well. I just want to apply it to neat coffee and it should just go. And people had also done the same thing for measuring caffeine. Yet again, differential pulse voltammetry doing pretty good, basically the same as high performance liquid chromatography. So not even going as far apart as the acids and the phenolics. Now we can do phenolics and caffeine like I proposed in my picture at the beginning. Okay, so what's the first experiment? You basically go and you make up water at the pH of coffee, and then you start creating a standard solution of chlorogenic acid. And you can very clearly see that as I add more chlorogenic acid, the peak grows in. Excellent. And as I add more caffeine, the peak grows in. But this isn't coffee. This is just a model system of water plus these compounds. It can also be used to look at other compounds. And I was excited about this because chlorogenic acid decomposes during roast. And it turns into caffeic acid and quinic acid. And I can see that caffeic acid very clearly shows up at plus 0.3 volts. So now we're getting that molecular level resolution on lots of different compounds, just as I'd hoped. So when the grad student came to my lab and said, this is working perfectly, I said, great, let's double the amount of caffeine in a cup of coffee. Let's show that it grows right in there exactly where we'd expect, that we get a caffeine level measurement on a cup of drinkable coffee. And they brought me back this data set, where they've doubled the amount of caffeine in a cup of coffee, and you're expecting to see this massive bump right here, and they are exactly the same. And you double the amount of chlorogenic acid, and you see nothing. This was a bad day. So this was 2023, January. So this is a while ago now. And it turns out that we could have actually saved ourselves some time if we'd read the literature. In 2009, someone had made the observation that those two compounds that we cared about happened to stick together in solution. And when they find each other and form an aggregate, you can monitor them by NMR, which is an organic chemistry technique that just basically says these 3 peaks belong to caffeine. And if they stay in the same place in the cup of coffee, then caffeine is in the same environment that it was floating around in liquid water as it is in coffee. They don't, they move. And they move, that means it changes the voltage in which caffeine responds to in a cup of coffee. So that was bad. Okay, so what do you think the cyclic voltammogram of coffee would look like? Well, a reminder here, we have to be able to drink it. And I told you it looks like, I think it's dirty acidic water. Well, it turns out it looks just like dirty acidic water. So when you start sweeping the voltage, you see the bumps for hydrogen absorbing onto the surface of platinum. It burns back off. There's the hydroxide layer. This is you get the point. So this is just dirty acidic water. And this got me really excited because we know a lot about dirty acidic water. If it was something completely new that no one had ever measured before, then I would have been really stressed because it would have taken potentially 50 years to get up to speed. But no, we know this. So remember here, this is hydrogen adsorbing to the surface of our electrode. So if we just scan this way, hydrogen adsorbs, we scan back, it desorbs, and we can cycle around like this. And from this, we can subtract the background that is associated with making hydrogen gas. And if we do that, what we're left with is a feature that looks like this. This must be coming from coffee because coffee is what is making the water acidic. So this is a coffee-specific feature, and we can back out parameters like the voltage in which the center of this feature appears, the peak current that is available for that feature, and integrate it, and that's the total amount of charge that's passed. And like dirty acidic water, every subsequent cycle, we pass less and less current in that space because our electrode is now getting coated in coffee stuff. So now we have two handles in one measurement. We have the amount of acid in solution is giving rise to the size of this feature, and separately, the rate in which it gets gunked up is telling you something about what's in the coffee, because that's what's sticking to the electrode. And what also we found was that this feature depends on concentration. So the more concentrated the coffee, the larger the feature. Well, that's excellent because you may recall that optical device needs to be able to measure concentration. And if we created something that couldn't do that, then we weren't doing at least as good as the optical device. So this result here suggests we're doing as good as the optical device in measuring concentration. And this one I'm going to show you says that we're doing much, much better because now we're getting molecular level information. So what's sticking to the electrode? Well, you can do a measurement where you create a very small piece of platinum that's sitting on a vibrating balance. And as stuff sticks to that balance, it vibrates more slowly. So you can use the frequency of vibration to tell you how heavy the electrode is. And note the size of we're talking about micrograms of material sticking. It's a very small balance, okay? What's happening here is as we start to polarize, you can see red dot goes to yellow. Yellow starts to get hydrogen adsorbing. Hydrogen doesn't weigh anything. It weighs 1, so you don't see it, right? And then at some point, when there's a critical amount of hydrogen on there, you can see mass starts to gain. And that's because hydrogen helps things, other organic molecules, I've drawn caffeine here, stick to the surface. And you keep going and more will accumulate up to a point where you start to burn off those protons, at which point mass drops very rapidly. And in principle, everything comes off the electrode. But in practice, we know that's not true because subsequent cycling shows that less and less current passes. But appreciate more or less this is what you could do. So if you want to know what's sticking, what you have to do then is just sweep the voltage down here and then go back to here, but never go to the voltage where it burns everything off. And then you just start cycling over and over and over again. And if you do that, the mass starts to accumulate more and more and more. And then you pull the electrode out quickly and rinse it off and measure what's stuck to the electrode. And it turns out it's caffeine and other stuff, but mainly caffeine, which means here's a picture of it. It's basically coffee stuff stuck to the electrode. So that's good because that means now that we can use the amount of current passed on the first and second cycle to make a statement about the amount of coffee stuff that's in solution and have knowledge that is mainly caffeine. So we have a handle on at least one molecule. So then if I change brew parameters like temperature, time, et cetera, I can now have a probe that tells me something about the kinetics of caffeine extraction. This is excellent. But we have a problem. I buy coffee from, I forgot the name of the local roaster here, but we buy it from the local roaster here. We buy it from someone in Eugene. They could look the same color, but they're going to have wildly different composition, not only because of the origin, the processing method, and all of that, but also because the way that you heat the coffee, the roast profile determines what's in the coffee. So in my lab, I then had to learn how to roast coffee. So we got this thing here. It's a glorified popcorn maker. The coffee gets roasted on this side, and when it's done, it falls over and ends up over here. And it follows along these temperature profiles. And so you can see shorter, lower end temperature gives you light roast. And if you go longer at relatively, just incrementally higher temperature for longer, it gets darker. Okay, so these are my roast profiles. And if you do that, and then you brew the coffee up using that cupping method that I showed at the beginning, where you just grind coffee, pour water on it, wait for 4 minutes, and then measure what's in that cup, you can very clearly see that light roast coffee has a lot more charge being passed in that region than dark roast coffee. And if you plot that as a function of concentration, so this is the charge pass versus concentration, and parse out the different roast colors, what you very rapidly see is that light roast coffee has a different gradient than dark roast coffee. So this is nice because now we have the concentration of the cup, we have the color of the coffee, which can be measured by taking a photo with your phone, and we have the amount of charge that's passed, which can be measured by just basically applying voltage and measuring charge. And if you pick any of these two, you can then predict the third. And if you deviate off of this plane, then something terrible has happened. That cup's probably not going to taste very good. So we need to go one step further. I'm going to see how many slides I got for you. Yeah, okay, I got about 10 more slides. Okay, we got to go one step further. Think about this cupping situation. The variables that you can control are mass of coffee. In other words, how much do you put in there? The mass of water. You can also control water temperature, the time that you leave that coffee touching the water, and finally the grind setting. And those are the 5 variables. Now, of course, there's one more. You could stir it or not, but we're not talking about that. We're talking about how we do it in the cupping system. So let's do a sanity check here about what this data on the right's showing us. So log TDS is the concentration in the cup. Okay, so this is as measured with that optical device. If I add more coffee to the cup and keep everything else the same, you would expect the cup to get more concentrated. That's this line. 8 grams of coffee, less concentrated. 20 grams, more concentrated. Okay? So that's how you should read what we're looking at here. The next thing I'd say is if you add more water, you'd expect the cup to get less concentrated. So you see a negative response here. What I want you to glean from this is that if you see the same type of response for any of the other parameters, note this is the peak current, this is that peak center of that voltage measurement that we made, then this is a good measurement for that. So here you go. So peak, this is the peak current that's passed, so the max current. You can see it basically responds exactly the same to the variable to the change in variables down here as TDS does, which means we can just do a simple single measurement quickly and measure the peak current, and that tells you the concentration of the cup. That is a good result because that's super easy to do. But there are other things that come from doing a design of experiments like this. So note this is a correlation plot for, is it correlated with the concentration of the cup or not? Peak current, we just talked about it, that it is. That's I right here. And indeed, you can see it down here. Peak current has a strong correlation with concentration in the cup. Other things do not, well, okay, so total current, strong correlation. Other things do not. So this peak center, this position here, it seemingly can move left or right a little bit. And you can look how much we're talking about. We're talking about it moving in the vicinity of like 0.01 volts. So not a lot of change in voltage, but it does not depend, it is not correlated with concentration. And this is the best result in my entire career, and I really mean it. Because what you're able to do with a good design of experiments is back out which variables are the most important in dictating these parameters. So let's go and look at this one again. This is the optical TDS measurement. And here you can see the most important thing that dictates the concentration as measured optically is how much coffee you use. The next most important thing is the mass of water, then the grind setting, temperature, and time. Okay? And I mentioned that this peak current is a good measurement for that. And indeed, it has the same, more or less the same dependence on variables. We're going to get to these interactions over here in just a second. But I do want to point out that total charge passed also more or less the same. This variable right here, which is time and grind setting together, interact. What that means is that if I don't include this mathematical interaction, I'm not going to be excellent at predicting TDS. Now let me go, I'll show you that down here, and then I'm going to go back one slide. With the inclusion of that, I'm able to predict the concentration of the cup for any parameter space that includes grind setting, mass of coffee, mass of water, brew temperature, and brew time, I can predict the concentration of that cup basically analytically. Previously, without that interacting variable, it was pretty damn good, but not perfect. It was at 0.95. We're now up to 0.992. So this is basically perfect. Okay, but let's go to the one that's not obvious. So this peak center, that is the voltage of that peak. Well, this one depends most on temperature, time, and grind setting interacting together. And the other variables also dictate it. But this is really complicated, right? It's all of these things together. But if you actually include all of them, you're able to predict peak center very well. Let's take a step back, though. Think about what temperature, time, and grind setting are. I showed you when I developed my mathematical model that coffee gets wet and it takes time for it to get wet. And once it's wet, it starts releasing compounds into solution. That depends on grind setting. If I make the particles smaller, then seemingly it gets wet quicker. So that's grind setting. Temperature and time. Do you remember at the very beginning I told you that there's a Nobel Prize in 1901 that said temperature impacts equilibrium constant and kinetics is when you decide to stop it? Those are temperature and time. To see that peak center depends on the three things that we've failed as an industry to account for forever, and it's most dependent on that, is an extremely good result because it means that we can use peak center differences to tell us about composition that come from things that we're able to control but not able to measure. So this is a big deal now. I'll give you an example of how one might use this. If I go to a farm and I get the farmer to brew up a cup of coffee and I'm about to decide to pay X amount of money for this cup, I ask him to brew it again but change one parameter, just one. And he brews it and now the cup tastes worse. What we're able to now use those two data points for is to feed it in directly into this model with that electrochemical measurement. And now we can maximize, so go the opposite direction to that result. We can maximize the cup quality, which means that I taste the cup and I say, I'm going to pay $2 for it. He changes the setting, it gets worse. I'm going to pay $1.90. He changes all of the settings and maximizes this to hit what he wants. And now we're looking at paying $2.50 a pound. So this is a big deal for producers because this means that we can take whatever parameter space they're operating in and take it to maximum quality as defined by their tongue. So it's inherently general. This is good. But what if it still tastes bad? That's the big problem. Well, I mentioned that at a given voltage, these molecules oxidize or reduce. We're basically applying a voltage and we're stealing electrons or giving electrons to molecules in coffee. And what's really cool, one of the first observations we made was I thought we made two identical espressos. They hit the same shot time. It was the same mass of water out. It was the same everything. But seemingly they had wildly different composition because if I applied 0.6 volt, I should see the same amount of current pass at 0.6 volt if the composition is the same. But espresso 1 passes a ton more current than espresso 2. And that's the voltage that this molecule responds at. So that's not good because that's saying espresso 1 has a lot of this, espresso 2 has not very much of it, and they were seemingly identical. Indeed, they tasted different. But the other thing you'll see here is that look how quick it's happening. So this measurement is in the vicinity of microseconds. But over time, this curve is decaying. And that's because once I've stolen the electrons from this molecule, I have to sit around and wait for more of those molecules to make their way to the electrode surface, run into it, and steal more electrons from new molecules. So we call this a diffusion barrier, where basically you sit there and wait and the molecules make their way. And if you stir it, then you overcome that barrier and you'll pass a lot more current. This molecule doesn't taste very good. So it'd be good to be able to destroy it. So we did this experiment where we just sat at 0.65 volt for a little bit of time, and we measured which molecules. So I'm not going to go into the details in great detail, but this molecule comes in different flavors. You clip that part off and put it here. It's a different molecule, but more or less the same. That's all these different ones. And you can see that if I sit at that voltage for different times, it converts selectively some of them, but not others. Which means we're not even being selective, but we're selecting for them because of the diffusion barriers. So that's cool. What about how it tastes? We took a panel of 57 trained coffee tasters. We applied these different voltages for this different amount of time, so short periods of time, really low voltages. If the number goes down, that is worse. So if the number is, if you see it going red, red in this case means improved or heightened. And so versus the unmodified one, overall quality for this particular cup seems to have skyrocketed with the application of 700 millivolt, or in other words, 0.7 volt, half of a AA battery for 30 seconds stirred. And this p-value is statistically significant, suggesting that of 57 trained tasters, this is a real result. In other words, people can really taste the difference. The quality has been improved in this particular coffee by applying a small amount of voltage. Why? Because it turns out that acidity seemingly did not change very much, but sweetness was heightened. Sweetness. It's a weird thing, but everyone likes sweetness, so seemingly applying voltage can modify flavors as well. Let me give you a broader picture for the implementation of this in other applications. Has anyone here, or does anyone here like Brett tainted wine? I'll say taint, that makes it sound bad. Brett wine and beer. Anyone had like a Belgian style? You're into it. Yeah, so me and you go to a bar and you're going to open this Belgian thing that tastes like feet and you're going to like it. And I'm not going to like it. But the molecule that's responsible for the thing you like can be electrochemically degraded into CO2 and ethanol very rapidly, which makes me happy because then you get your weird like gym sock beer and I get a more alcoholic bubbly beer and we're both happy with the exact same beer. So you just take your piece of platinum, you stick it in there, you apply about 1 volt for about a minute and it's done. Let me give you another example. I'm into bourbon, big time bourbon situation in my office right now. Old bourbons have chemically dissimilar compositions to young bourbons, but the molecules are more or less the same. It's just they've undergone different chemical reactions, oxidation, this sort of thing. It applies to wine as well. One thing you can do is you can rapidly age bourbon by simply oxidizing it, by sticking platinum in and positively polarizing the platinum. And you can take bourbons that taste like 4-year-olds and take them up to tasting like 12-year-olds. We do it all the time. It's sort of a party trick. The other thing you can do is detect counterfeits. If someone claims a 6-year-old bourbon and it has this signature, but it's actually a 2-year-old, you can see there's pretty wildly different composition in there. You can do it electrochemically. We're not the first people to think about this. Hopefully what I've tried to give you a sort of a broad spectrum of what we're talking about here, but the key thing, if you had to take away anything, is I have a podcast. It's extremely hard to find, okay? But really, if you add a little bit of water to your coffee when you grind it, static goes away. And by doing so, that allows your water to access more of the coffee in most brew formats. So this is a good thing. Try it yourself, add 1 drop. The manifestation of this in my household, I weigh out 20 grams of coffee, I wet my hand, I let it drip off until I got like 2 drips left, and I like shake it at the coffee and that's it. Because I'm like you, we just got to get it done in the morning, okay? So add water to the coffee. Coffee is dirty acidic water after you've brewed it. And I was trying to show you that we can use electrochemistry to do as well as that optical device in terms of measuring concentration, but we can do even better because we've now been able to parse out how different variables in brewing coffee actually impact composition by monitoring that peak center, EP, which is the voltage in which coffee responds. I gave this example here of all these different interacting variables. This is a really powerful statistical tool. This is not only applied to coffee. We're looking at applying this to all sorts of things. So I'm happy to talk more about design of experiments if you'd like. All of that is to say, I know we covered a lot of stuff. We basically covered all of Gen Chem in about 1 hour and 10 minutes. So with that, I'm sure that you're done. I'll let you tap out here. I want to say, come visit us. That's the best way to get exposed to this. If you're ever in Eugene, let me know. Email me. I promise you, I'll be very happy to host a coffee tasting that will be illuminating, hopefully. Hopefully you enjoyed this. I'll happily take questions. Thank you.
Thank you, Dr. Hendon. If anybody has any questions, if you would just raise your hand and I can bring you the microphone so our online listeners can hear. 1 second.
So was the third thing I'm supposed to do is hit it with a 9-volt battery before I drink it?
You can do that, but be careful with the electrode material. So I gave the example of platinum throughout today. You need to use a metal that's not going to corrode So if you were to take a piece of iron and you apply the wrong voltage to the iron, you could basically rust the iron into the cup. So what I'd recommend you use, 9 volts, a little too hot, maybe AA, 1.2 volts is good. Gold. Gold's excellent. So just jewelry. In fact, I didn't know that it was like the head of research at Nestle, but she was wearing a lot of jewels. And I gave this seminar and I had my device to apply voltage, but I didn't have my electrodes. And so I said, well, if you want to see it, give it to me. And she took off her earrings and her bracelets and I strapped it on and we just did it with her jewelry. It worked perfect. So it's a relatively low barrier. I know gold and platinum are expensive metals, but there are other, graphite from a pencil works fine as well. Yeah.
Thank you. We've got another question. And if you have a question online, please put it in the comments and I'll try to ask it for you.
So, what's your email?
My email? Yeah, that's good. I should have put that on the end of it. That's on my to-do list, is make the last slide of my email. Here you go. There. I can see the chat here too. Only one comment from someone named Eggs and Bacon.
So I've noticed if I leave coffee for a long time, it tastes really bad.
Mm-hmm. How long?
Not long.
Brewed coffee or whole beans?
I've only noticed for brewed. I wouldn't know for other kinds, but is that my imagination or is it changing what molecules are dissolved? Are they evaporating out? How would that happen?
Yeah, so if you can smell something, the molecules are being lost into the universe. And so if you're sitting there with a cup of coffee for quite some time, you're losing molecules actively into the room and wherever you're drinking it. Over time, that will have a negative impact on flavor. There are other competing chemical processes that also occur. So oxidation is a reaction that's slow. It's with oxygen gas in the atmosphere reacting with organic molecules. That can also happen over time. Typically, oxidized things don't taste that good. I have had the shared experience. It's not your imagination. They often come out tasting kind of caramelly, like a cup of coffee that's been left for a while tastes kind of caramelized and sometimes more bitter. There's an element of also temperature, the temperature in which you're tasting it again. The human body is much better at perceiving flavors when it's closer to your body temperature. And we've evolved so that we can perceive bitterness, heightened bitterness at high temperatures, because typically things that are bitter are going to kill you. And so it's good to be able to taste bitterness at all temperatures so you don't eat the wrong leaf or whatever, right? So typically then you're going to taste a lot of flavors in cold coffee that's been available for some time that you wouldn't have tasted in the hot cup. And a lot of the coffees are not calibrated to taste good once they've sat on your desk for an hour, because the roaster is not thinking about that. A good experiment to do is to try hot sake and cold sake in a Japanese restaurant. Ideally, if they have the same, they have wildly different flavor profiles. Yeah.
Does anybody else have some questions? Hold on one second. I'm going to work my way back to the front.
I can also, yeah.
So I am from Brazil, and I remember my great grandma making coffee. It looked almost like a sock.
Yeah.
And you almost boil the water, grind the coffee, and so my question is, what equipment does the really, really expensive one, is that worth it? Or can it be pretty simple and have a great cup of coffee?
Yeah.
What is your opinion? Like, how do you make your coffee?
Yeah. So first of all, for those that are less familiar, Brazil's the largest producer of coffee in the world. They can basically produce as much coffee as we need. The Brazilian coffee market is also highly mechanized. So they're one of the most developed and sophisticated coffee producing regions. I've never had the luxury of having Brazilian coffee in Brazil. So I haven't had the shared experience. I've only ever had Brazilian coffee outside of Brazil. And I've had the SWOCC coffee before. So why I'm saying all this is because excellent coffee doesn't require any equipment. You just need to grind it up and add water, hot water, and drink it. And in fact, even if it doesn't taste good, it can still be excellent. I have plenty of examples of that where you have one of your most memorable cups could be one that you shared with your grandmother, not necessarily remembering the flavor profile per se, but remembering the environment that you shared that coffee in. You don't need to spend a lot of money on brewing equipment. However, if you wanted to, you should buy a good grinder. That's the most important thing to spend money on. Then just make French press where you just submerge the water, the coffee in the water, and that's it. But other people have different opinions, but I think the industry has converged to this idea that the grinder, if you're going to get into it, spend a couple $100 on a grinder. It's going to be a big upgrade.
I've
got two here.
okay.
Three.
Yeah, I also have some online questions.
Oh yeah. Well, here, do you want me to hit one online one first?
Sure.
Yeah. Okay. So one of the online contributions here says, if I'm not a big coffee person, try using freezing, zapping, adding some water to my beans. Would it make a large difference? Is it going to elevate them to being a coffee lover? I would say of the things that you need to try, applying electricity to your coffee is a fringe technique at this moment. Given that I literally am the only person doing this to modify flavor in the world. So don't do that. Do not start strapping a car. Don't jumpstart your coffee with your car. Freezing coffee makes a difference if you use a burr grinder, one that allows the coffee to exit the grinder once it's sufficiently small. The whirly blade grinder where you push down and it whizzes around, you don't see the benefit as much because the coffee can in principle still get further fractured in there. So the real benefit of adding water and adding and cooling it down only really applies to burr grinders where coffee goes in, grinds come out. But it's a good question. You know what will make you a coffee lover is come by my lab. I'll give you an experience that you can't even, you wouldn't know it was coffee.
So you brought up my question, which is what kind of a coffee grinder do we recommend? What did you come up with?
Yeah, so at home I use a conical grinder, which is basically imagine a glorified drill bit. The drill bit is sitting inside a bezel. The bezel has teeth that run, let's say, counterclockwise, and the drill bit has teeth that run clockwise. And if you pull the drill bit out, the gap at the bottom gets bigger, so the particle size distribution shifts to coarser. You push the drill bit in, and in principle, all the way in, it would make metal contact, so that's not good. The cheapest one that I use is the Baratza Encore, and I think they go for like $140 now, and it's fine. I mean, it's not great, it's fine. Yeah, it's a conical burr grinder, so it's got stainless steel burrs, yeah. They do make cheaper burr grinders, so you've probably seen some in Target. One thing you pay attention to is make sure the burrs are made of metal. It seems obvious, but there are cheap burr grinders where the burrs are made of plastics. Thermoset plastics pose all sorts of problems. First of all, they blunt in like 6 months, but then you also have microplastics making their way into the coffee, all sorts of stuff. So yeah.
Okay, I have one more online. And thank you again, Caters House, for your nice comments earlier too. This next one is from the person that goes by eggs and bacon. Theoretically, rather than adding sugar, could the addition of salt positivity charge the coffee, making it sweeter? To add to my question, what are some trade-offs?
Yeah, so it's a common this is a sort of a common paradigm of adding a pinch of salt to an espresso, and it affects the flavor. It definitely does. I don't know why it does. I do know that it affects the flavor. Adding sugar also affects the flavor. Basically, anything you add to espresso affects the flavor. But I will say it probably has to do with your perception rather than doing something chemical. It's probably like there's a heightened, you taste more salt, you're going to have a heightened ability to taste other flavors. This is extremely complicated. People in psychology have dedicated multiple careers worth of effort to understanding human taste perception and smell perception. Now, I'm not an expert in that, but that is a good question and something that's worth pursuing.
And Caters said that they're going to try to stop and to see you, and next time they're in Eugene. Does anybody else here have questions?
It's coming. I see it.
You mentioned that one of your goals is for countries who do a lot of coffee production, like that this research can really impact them. Do you collaborate with any roasters or farms?
Yeah, so I don't, oh, no, I don't have the slide today that highlights all of the roasters that have worked with us over the years. It's a lot. The lab doesn't buy coffee anymore. We go out once a year and solicit donations, and we have a deep freezer where all the coffee is sealed in vacuum bags at 100-gram vacuum bags and stored until we need them. Roasters, it costs us, all of us, a lot of money to buy coffee. You know, it's 5 pounds of coffee is not cheap. And if you have to do it a lot, it gets very expensive. But from the roaster's side, 5 pounds of coffee is basically nothing. It's, you know, it's a handful of dollars. So I've been fortunate to be on the receiving end of many charitable donations over the years. And I usually show that slide with all of the different roasters. For them, this is the way that they feel like they're engaging in science and helping the community and the broader ecosystem of coffee is by giving us coffee to work with. It also overcomes biases that I have because I have a very specific preference for washed Ethiopian coffees. And if I had my way, I'd only buy washed Ethiopian coffees. But that's not all of coffee. In fact, it's not even a fraction that matters. What matters much more is the Brazilian market and all the other paradigms that don't align necessarily with my flavor preference. Those contributions are acknowledged in the scientific papers. Well, we do our very best to be as rigorous as possible because we know people read these papers and actually use this stuff. And I want to make sure that we are not only doing good science, but also being a good example of what good science looks like. So reproducible, as transparent as possible, provide all the data, this sort of thing. And it's not only because of me, it's because of the roasters and everybody, all the people who have donated time. That's a good question. Finally, here we are.
Can you hear me? Yeah. You said misting your beans. You didn't give a volume of beans. Are you talking about whatever you're going to put in the grinder, a very small amount?
Yeah.
To a small mist of water?
Let me go to that slide. So first thing, you should probably weigh the amount of coffee you're grinding, and then you should weigh the amount of coffee you're grinding and weigh the amount of water you're using. That's a starting point. But let's assume you're doing that. The x-axis here is in microliters of water added per gram of coffee you're using. So that's a kind of a tough, that it's hard to get your head around what that value means. Let me see if I have it stated in a different way. I don't know if I have it in here. It shakes out being something like 0.2 milliliters of water, which is 4 drops per 20 grams, puts you in this region around here. So 20 grams is about like a sizable handful.
Okay, but add on to that, are you working with any manufacturers? I have a spin, if you know what that is.
Yeah.
And it's intimately adjustable, and it'd be very simple to add a mister on top of its grinder.
Mm-hmm.
So are you working with manufacturers, or is anybody coming out with the next great coffee machine?
Well, okay. So we're not presently working with manufacturers because we hold the patent. So for them to work with us would cost them. They don't want to do that yet, but there are people who do want to do that. I don't usually patent stuff. I usually put it out there publicly so no one can patent it. And that also makes manufacturers not want to work with us. So I've always done this thing. I'm not very good at business. I'm good at science. And so I have more enterprising students these days. And the more enterprising students are seeing many more business opportunities coming from a lot of the stuff that we've been talking about. I mean, just think about the bourbon example at the end, right? That's endless money. I don't monetize that, but the students are interested in that. So that's a new thing. That's something that I received tenure 2 years ago. And once I've done that, now I can start doing weird stuff like this. So we're going after more of that. But for now, I don't have an industry partner on the misting. Yeah. Funnily enough, in the back of my car, I do, but
Any other questions? And eggs and bacon said, thank you.
I have seen where people pull espresso shots and then they pull them directly on top of frozen steel balls.
yeah, the golden snitch.
Yeah. Yeah, how is that rapid cooling affecting the flavor of the espresso?
Yeah, I'm glad you asked that. So I want to point out something that happens in coffee science more, I think, than basically any other food science is the weaponization of science to sell a product. So the premise of this is that there's a cold ball you put in the fridge or freezer, and espresso is losing volatiles pretty quickly. It's because there's a lot of CO2, and so it's basically driving out things out of the cup, out of the liquid as soon as it comes out of the portafilter. And if you can cool that down, and then the idea is maybe you can condense more of the volatiles into the liquids for that short period of time where it takes you to brew the cup and then bring it to your mouth and taste it. And in the studies that were performed to substantiate the claim that that thing worked, almost all of them yielded a up to 5% difference. In other words, no difference, except for one example that yielded an anomalous 40% difference in volatile composition with and without the golden ball. They've used that 40% in marketing, but that is what I would say. I mean, so first of all, it's not statistically significant. It's an outlier. Could have come from anything, right? But more importantly, they weren't controlling for differences in espresso composition. Like they weren't measuring that thing that I showed in this slide. So they were thinking they're pulling the same shots, but the shots have different composition. So it's really, really difficult to make the statement that they were trying to make. I'm not saying that they're wrong. I'm saying that you can't, unless you know what's in that espresso, you're fighting an uphill battle. So you got to be careful when you read science about coffee and science in general, that you make sure you go into and think about it like, what are the limitations? We all have to sell our impact to get it in better journals and to get more funding and more notoriety, but there is limits to every study, and coffee is a particularly bad field for this.
Awesome. So the test that you do that you find that peak voltage, have you thought about possibly trying to design like a all-in-one device that could be sent or easily made by the growers?
Yeah.
And they could test it at like on site, and they know the worth of their coffee from that.
Yeah. So the device that you need to build to be able to do this is basically running a multimeter that you would get from Home Depot or similar in reverse. So a multimeter is measuring voltage, right? And this one here is applying voltage, measuring current. So the device is actually very well known. You can build them. Some schools use the building of the device as a laboratory for general chemistry. It's just a potentiostat is the name of it. And so we have actually usually cite several papers that talk about building your own potentiostat. It's not difficult. It's a great activity for those that are electrically minded. You should try it. What's more difficult is making a good measurement here. That takes, at this point, we don't have the method that's, I guess, reproducible enough to roll it out into the top of a mountain, for example, to be able to teach someone, oh, this is how clean things need to be, et cetera. So we're not quite at the stage yet where we take this into or throw it out into the wild and see what people do with it. But the papers are under peer review right now. And by the time they actually show up published, will be the time that we have that all figured out. So we can actually be sure to give good, safe advice to people who are going to use it.
Awesome. Thank you. And then my last question is going back to the very beginning when you were talking about the water at Bath. Is there a certain type of water that should be used? Should we be using pure, like distilled water, or should there be some mineral content in the water?
Yeah, I didn't show the ideal water chart, but imagine that you want some minerals in there, because if you don't have any bicarbonate, then the coffee comes out very sour. So you want there's a critical minimum amount that you need of this, and it is comparable to tap water in Eugene, Portland. I don't know what the tap water is here, but relatively soft water does enough of this. You don't want too much chloride in the water, because that will corrode steel. And most coffee brewing equipment and boilers and kettles and whatever are made of steel. So chloride's not good for brewing water. And then finally, the positively charged species, calcium, magnesium, that sort of thing, we think that those are good. I showed one picture of it here if you up the cationic concentration in a cup of, or in brewing water, it makes the water more polar. More polar water tends to favor extraction of more polar molecules. More polar molecules in coffee tend to taste good. The non-polar stuff is what gives rise to the ashy bitterness that comes out of coffee. So if you brew with soft water, you tend to find you can get some more of the ashy bitterness out while leaving behind some of these larger but polar molecules that have good mouthfeel, good flavor. So these are some nuance in this, but basically you don't want it too soft because then you get sourness. You don't want it too hard, then you wipe out all the acidity and you have a problem with lime scale forming. So somewhere in the middle there. I'll give you homework. Buy Evian bottled water and brew coffee with Evian bottled water. It'll be the worst cup you've ever had in your life. Then do exactly the same thing with soft water. And you can pick any of your favorite soft waters, perhaps tap water if it's soft here, I don't know. But soft water, you can do like smart water is soft water. Brew with that, and you'll see that the flavor differences are remarkable. So even the untrained taster can really tell the difference. We're talking major differences. This will be a revelation. So a final anecdote on that. When I was deciding where I wanted to move, I did consider the water quality as a factor in the place that I wanted to live. I don't know if anyone else has had this same, you've also felt this way? Yeah. Where were you before? Yeah, it's awful. It's awful. You can't drink that stuff. You can't wash your hair in it. Yeah. Yeah, it's awful. Yeah, so we were thinking a lot about that. So when we got to Eugene, it was nice and soft. It was basically, we don't do anything to our water, even though I wrote a book on it. I just use what's coming out of the tap there, filtered over carbon, because it's easier than designing these fancy waters that we're talking about. But in Santa Barbara, you'd have to do something. Yeah.
Did anybody else have any questions?
Yep. Carbon. Yeah. So the question for those online is that this is one of the few places to use chloramine to treat water. It's very effective at the job that it's doing, but it does inevitably impart a flavor that I can taste, and I guess many people can taste. Activated charcoal or carbon filtration is very good at removing chloramine. Activated charcoal actually typically comes from the husks of coconuts that have been roasted, because there's no use for a coconut husk. So it is a secondary market that ends up yielding a product that we use for water filtration. So I'd encourage, that's what's in the little black beads in the Brita filter are made from coconut husks. So I'd encourage you to get a activated charcoal filter. Brita is one, but there's endless examples of these on the market now. And it will do a very good job of cleaning that up for you.
Thank you. All right. Well, I want to say thank you again to everybody for attending this great event tonight. And thank you, Dr. Hendon, for coming over, and Professor Morelli for arranging all of it as well. Thank you again.
Thank you. Oh, I did it.
You go to get coffee all the time? It sucks. It's the temperature of the coffee they're giving you.
That's it. That's it.
So you got to figure out the exact temperature and tell them, hey, I want it at this degree. And you know,
That's what my mom does. She's